So I'm going to introduce Ritesh to you and tell you a little bit about his background. So we have hired Ritesh to be a senior faculty specialist in my unit, and he plays two roles. First of all, he helps with the research administration, and the second thing he does is adds expertise and depth to our modeling expertise that's available in this department, but also he adds depth to the climate change expertise. So Ritesh received his PhD, undergrad and master's degree from Mississippi State University in Ag and Bioengineering, and PhD degree in Biosystems Engineering at Auburn University. And then he was a postdoc at Penn State for a year. And then for last couple of years, he has been postdoc at Essex. All of you know Essex, where he did a lot of work. So Ritesh has expertise in climate change area. He is a really good modeler. Not only does he use large scale, regional scale models, but actually goes to the source code and improves the model. And Ritesh is going to talk about, one of the big projects he's doing is implementing a wetland model inside the SWOT model, which is a large scale hydrologic water quality model. He's also adding carbon module, improving the forestry representation in the SWOT model. So he's a really, really great modeler with lots of expertise in modeling and climate change area. So with that, I'm going to turn it over to you, Ritesh, and so that you can present what you have done and what your expertise is. But I would also say he is already collaborating with a lot of you. He's collaborating with Adele, he's collaborating with Masood, then helping on a lot of different projects, and also working with Kate Tully and some other people. So he has already hit the ground running and engaging with a lot of faculty, but he's open to collaboration with all of you. So if you see that you have any kind of opportunity to collaborate with him, Ritesh would be happy to collaborate with you. With that, Ritesh, it's all yours.
All right, thank you, Dr. Shrivastava. And again, thank you for wow, this is bright. For providing me, with the opportunity to present, in this seminar. So as Dr. Shrivastava mentioned, right, so I am a senior faculty specialist in the College of Agriculture. I started in April. The research part of my position, in here, anyways, it's focused on doing climate-related research, and basically helping and in any research within the College of Ag, related to climate, right? So the presentation today, I'm not going to go in detail of any of my research, but basically I'm going to provide an overview of what climate related research that I've started at, where like in my position at MAES, as well as other projects that I'm, currently involved in, but that has the potential to be applied. And maybe there's a need for those to be applied, in the mid-Atlantic and as well as Maryland, for climate change impacts, mitigation and all that stuff, right? So, okay, so I got to do this. All right. So we all know how critical of an issue climate change is, especially in the last couple of years, right? Climate change is a critical issue even in the agricultural sector, right? Even in Maryland, which is close to $2 billion industry, right? Climate, due to climate change, extreme flooding, droughts, right? Those can lead to loss of production, right? Along with that, saltwater intrusion, due to sea level rise, as well as from the underground water sources, that can lead to loss of agricultural productivity. Along with that, the salinization of groundwater sources can lead to a loss of irrigation water sources in Maryland. So there's like these are only some of the aspects that is impacted by climate change, right? Now, to two things that I need to do. All right, so to basically evaluate the impacts of climate change, on any region, the precursor to that is basically understanding how climate is changing and is projected to change, in the future at a high spatial resolution, so that we can, perform those evaluations at a high resolution and, develop mitigation as well as, adaptation, practices for the localized regions, right? So along those lines, so my presentation today is going to be focused on like three sections. Basically, the first part, I'm going to talk about a climate related research, basically identifying appropriate climate data sets, as well as and then evaluating the trends of different climate indices in the Chesapeake Bay. That'll be the first part. And then the second part is going to be the application of climate data sets, right, past as well as present, to evaluate how these climate is impacting surface and groundwater hydrology, water quality, carbon, which is the new big thing now, right? And then the third part is going to, basically touch on how, the project that I'm working on, where we are looking to improve the physical representations, of many processes within the model, so that we can, when we do these estimations using the climate data sets, we can reduce the uncertainty and, basically increase our right confidence, in the estimates, for our management practices and all that stuff, right? So the first thing I'm going to talk about is the evaluation of gridded data sets, for the Chesapeake Bay watershed. Now, we all know climate data is the precursor, to doing any climate change related evaluation, right? And for that, the best climate data is basically observed groundwater station, like, observed weather, stations, right, that are quality controlled. Now, if you look into the map right on this right here, all the blue dots represent all the NOAA, like, uh, weather stations that are available within the Chesapeake Bay watershed, right? But if we do a quick filter of, like, if of like 25 years of continuous data for temperature as well as precipitation, we come down to 40 stations, right? So climate data sets in itself is, like, although we would like to use observed stations, we cannot use climate and, like, ground stations, right? And that is why we need to rely on gridded climate data sets, for performing, like high spatial as well as temporal resolution, evaluation of climate, right? But as these grid climate data sets are estimated, based on these observed estimates as well as other methods, it carries a high amount of uncertainty, right? And it is always, so that is why it is important to understand the uncertainty that are associated with this gridded data sets, as well as identify the best data sets that could be used for the reason, before doing any analysis, right? So the first part of my work, that I started here is, I'm going the wrong way, is, so that's the one I'm touching, right? And so we looked into the 7, most widely used climate data, gridded data sets, for climate change analysis, and then we evaluated its skill, to basically replicate temperature, like precipitation as well as the extremes, in the Chesapeake Bay watershed, right? And so the 7 data sets that we calibrated are listed right here. Global meteorological forcing data set, PRISM, DAMET, LIVNA, NLS2, ERA5, as well as NCLIM grid daily. And if you look at the methods, there are different ways that these data sets are estimated, right? Some are just based on statistical methods. Some use just reanalysis, which is basically feed the observed stations into the models and then use the model outputs to get a, like, spatial as well as temporal resolution. And others, use a combination of statistical as well as reanalysis, right? For example, NLS, it uses a statistical precipitation data set, but that is fed into a model, and then the model provides the other climate variables like temperature and then relative humidity and all that, right? And of course, the other thing to consider is the temporal availability as well as the spatial resolution of these data sets, right? They vary greatly from 1 kilometer grid to more than 28 kilometers grid, right? So this graded data sets, what we did was we compared against the observed NOAA GHCND stations, basically station data, right? And as I mentioned before, we did the evaluation for temperature and precipitation along with these extremes, right? Now this is a plot that you have seen right here. I mean, like already seen before, right? So we basically, when we did the filter of like at least 25 years of continuous data from 1981 to 2020 with temperature as well as precipitation, we landed 40 stations. So all the evaluations were done for these 40 stations, right? And so the way we did it was because for the gridded data sets, we chose the grid that had the closest, that was basically within or closest to these stations, and extracted the gridded climate data for the time period for which the observed was available, right? And then we did the evaluation. For the evaluation itself, we did a basin average evaluation as well as evaluation at each of these grids, so that we can look into how it's how these different climate data sets like represent the or capture the climate, the observed climate variability in Chesapeake Bay over the whole watershed, as well as for these different stations, right? So first, we'll look into precipitation, right? So the figure on the left right here is called a Taylor diagram, and most of you might already know it. And then it provides a very easy way of comparing multiple data sets, right? So if you look into the plot right here, the x and the y axis represent the standard deviation, right? This black dotted line, it represents like correlation, r squared basically, and that is like how it's distributed. And then the yellow line represents the RMSE, right? And we compared against the observed data set. So the observed data set basically has, like 100%, like, a correlation of 1, its standard deviation and RMSE of 0, and then all the other colors represent the different gridded climate data sets, right? So and of course, this is a basin average evaluation. So when evaluating at a basin average scale, what we can see is that enclave grid, and of course it might be difficult to see, but prism and enclave grid, like right here, they perform the best in capturing the overall precipitation of the Chesapeake Bay watershed. Like GFMD, there's the it is the worst, and others are in between, right? But when we are evaluating climate change impacts, we are mostly worried about the extremes, right? So we want to make sure that these data sets are also capturing the extremes of the precipitation. So what we did, going the wrong way. So what we did was, so we identified basically the 95th percentile precipitation from the observed data set, and then we, extracted the corresponding, values from the gridded data set, and then we did a similar evaluation for just the extreme precipitation values, right? And when we just evaluate the extreme precipitation values, we can see that the model scale already goes down, right? So from an R square of more than, like 0.9, it goes to slightly less than 0.8, right? The RMSE also increases, but the spread is still similar, as compared to the NOAA data set. But even in extreme precipitation, although the scale has gone down, we can see that enclave grid and prism still perform the best, right? And then DAMIT and then GMFT, they are among the worst performers, right? Now that was just basin scale evaluation, right? And after that, we also wanted to see how the gridded data sets capture the spatial variability basically at each of the stations, right? So what we did was we plotted a box plot of R square, mean absolute error, and then percent bias, of basically for the different data sets, right? And then when we look at this bar plots right here, we can see that as compared to the basin average, when comparing for each station, the range of the skill basically, right, in capturing the observed data set, it increases widely, right? So the R square, although the median R square is close to 0.75, the quantile is much higher, from close to 0.25 to even like 1, right? The mean absolute error, it also shows the range, and then the percent bias also shows the range, right? But even here, we can see that although there is a high range, enclave grid and prism still does the best in capturing the observed data sets for the different stations, right? And so when we focus on the P bias, we can see NL dash. Now this is a widely used data set, that's what I want to point out. It seems to underestimate precipitation a little bit, right? While prism and then enclave grid as well as LIMNA do a good job. After that, we wanted to always going on the wrong direction, sorry. So after that, we wanted to basically see how these different data sets are how do they perform for the extreme precipitation using a scatter plot, because that can tell us it's if it's like overestimating, underestimating, and how it's performing, right? So when we compare the 7 different data sets just for the extreme precipitation events, we can see that most of the data sets tend to underperform, underestimate the extreme precipitation events, right? So the value from the gridded data set is always lower, seem to be lower for the extreme events, right? But even in here, prism, enclave grid, right, they tend to capture the best. So even for extreme precipitation values, they do a good job. After that, we move to temperature, right? So when we temperature, and first we're evaluating the maximum daily temperature. Now again, looking at the tail diagram, we can see that all these different graded data sets, they perform much better in replicating the daily maximum temperature, when compared to the precipitation values, right? So if you look at the dots right here, so in here, contrary to the precipitation, LIBNA performs the best, and then followed by enclave grid and prism. But again, if you look at the correlation, it's high, close to 0.99, and then the R square, the RMS is less than 2, right? And so all these data sets are performing fairly well. But again, even for precipitation, GMFT had the worst performance. Okay, so when we move again, again, as similar to precipitation, we are interested in the extreme in the extremes of the temperature as well, right? So when we look at the extreme temperatures, again, the correlation again, slightly goes down, but again, they follow the similar pattern, right? And Jesus, sorry guys. It's like I can't turn, like, this doesn't work for some reason. All right, yes, then we do a scatter plot evaluation again, just to evaluate if the data set is performing, like if it's underestimating or overestimating these extreme temperatures, right? And then, again, from the plot, we can see that, the most extreme temperatures, these, like most of the gridded data sets are underestimating, right? So it's not as high as observed, like except for Prism and Enclave grid. They do a fairly good job of capturing even the extreme daily maximum temperatures. We did similar evaluations for daily minimum temperatures as well, and I didn't show you and the most of the plots, like the Taylor diagram, the box plot, they follow a similar distribution, so that's why I didn't show you that. This is the one. Yep. Oh, I'm slow. I skipped, so that got me. Is it the other? Geez, this is really confusing. T max. This is T max. Oh, maybe I was showing you the wrong place. So this is the bit for center then, right? But we only, I'm only showing you this way. Okay, showing you, the extreme T means basically, right? So like when we plot the extreme T means, basically like, lower than the 10 percentile, what we see is that again, the for the daily maximum temperature, like the gridded data sets were underestimating, right? So it was lower than it was observed. Similarly, for the daily T means, it is underestimating. So the gridded temperatures are not as low as it was observed, through the stations, right? So like as you can see here, these are all overestimating, or like basically like it's the T min is not as low as observed. But again, Prism and Enclave grid, they do a good job in capturing this. So we're going this way, right? Okay. All right. So because the when we evaluated the spatial, like the distribution of R square, like p bias and MAE for the different climate gridded data sets for each station, we saw a range, right? So what we also wanted to do is we wanted to spatially evaluate the distribution of these the skill, right, R square, MAE, and p bias, to make sure that there were no specific regions within the Chesapeake Bay where these gridded data sets were performing like really poorly, right? So we plotted the spatial distribution, and in here what we can see is that the R square, MAE, and RMSE, they are distributed randomly, right? So there is no specific regions within the Chesapeake Bay that where these gridded data sets are not performing well. So that's a good thing. So at the end, like to sum this up together, so Enclave grid and Prism data sets were the best data sets that we could be used for evaluation, right? So like considering the precipitation, temperature, and even the extremes, right? But among those two data sets, Enclave grid has a temporal coverage from 1951 to present, right? And then Prism has a temporal distribution of 1980 to 2020, so you could consider that. Now having said that, these data sets are limited in what they can provide, right? And so they only provide temperature and precipitation. That is why I went back to NLDAS. NLDAS provides a range of other data sets, right? Like relative humidity, solar radiation, wind speed, those which could be critical when especially like providing climate forcings to hydrological models. And that is why NLDAS is like used a lot, right, for evaluations. But when what this shows us that when we evaluate results using climate, like using NLDAS data, we need to understand that there are higher uncertainties when we're evaluating the extremes, right? Especially like say like stream flow, right? Or like so those kind of things we need to be careful about when using these data sets. So after identifying the appropriate data set for evaluation for the Chesapeake Bay, the next thing we did was we looked into climate indices. So from 1950 to let's go to the next slide. Yeah, so what we did was from 1951 to 2020, like we evaluated climate indices, right? So Enclave grid, because it has a resolution of around 5 kilometers, so there are like 10,752 grid points. So for each of the grid points, we evaluated precipitation and temperature indices, as well as a significance in trend, like are the trends significant, and what is the magnitude of the trend, right? And that could be critical because it will provide a very high spatial resolution indication of where these different indices are changing, and that could tell us like from an agriculture or a water management point of view where where we need to focus on, right? So that is what we looked into this way. right? I'm just touched on that. So these are the precipitation indices. In total, I evaluated 28 precipitation indices, right? So these are, total 28 total precipitation and temperature indices, of which 14 were precipitation. Now, so these are different indices, right? The total precipitation, like precipitation days, heavy, heavy precipitation days, very heavy precipitation days, like the maximum consecutive dry days in a year, maximum consecutive wet days in a year. What is the total annual precipitation, that fell as extreme precipitation, like that's this value right here. What were the number of, like count of days, that fell as extreme precipitation. We also looked into the simple daily intensity index. We looked into monthly maximum like 1 day precipitation, 5 day precipitation, and we also calculated, a standardized precipitation index, which is basically a drought indicator, right? Then we move to temperature, and these are the indices that we calculated: frost days, summer days, icing days, like these right here, right? Now I'm not going to present the result for all of these, but we have the results for this. I just finished this, so if somebody wants to discuss this further later, I'll be happy to do that. And I'm only going to present some results, right? So first, looking into precipitation. So in the so the graph right here, it shows basically the gray line, which seems like a range. It's basically the time series for each of the grids, right? So that's the for like it represents each of the grid. The red line represents the basin average of the change in so we do this, and how do I hide this? High floating middle controls. Okay, sorry. All right. So we're looking at total annual precipitation, right? So gray line represents each of the gray time series represents each of the dots. The red represents the average. This dashes represent the decadal average, right? And so what we did was for the whole basin, we calculated the significance using a non-parametric man-candle test, and then we also calculated the trend in the magnitude of the significance, right? So we can see that over the whole Chesapeake Bay watershed, there is a significant increase in total annual precipitation from 1951 to present, with an annual magnitude of 1.87 millimeters per year, right? So we can say that precipitation increasing, but it's critical to evaluate spatially as well, right? So that's what. So the figure on the left right here, so as I mentioned before, so I had calculated, basically evaluated the significance of trend, right, for each of the dots, right? So the figure on the left indicates the region where the trend is significant, right? And so we can see that, especially if you're focused in Maryland, there is a significant increase in, precipitation on the central Maryland, and then on the right, we can see, the trend in basically the trend magnitude, right, the millimeters per year. So the trend, it's basically from 0 to close to 5 millimeters per year, right, with the high increases being on this region and this region right here. After that, this way we look into total annual extreme precipitation, right? So we know that precipitation is increasing, but it'll have different impacts if the extreme precipitation is increasing or if the general precipitation is increasing, right? So when we evaluated the total annual extreme precipitation, basically the amount of precipitation that fell as extreme, for any given year, we see an increase as well, right? So when we evaluate the basin average, we see an increase. And when we evaluate it especially for each grade point, so the significant increase is observed in the northern portion of the Chesapeake Bay, as well as some portion of the lower Chesapeake Bay, and in some part of the Maryland, right? And this is the trend in the total annual precipitation. Similarly, we also looked into the number of annual days with extreme precipitation, right? And again, it follows similar trend to that of the total precipitation, with significant trends in this region right here, and that is the magnitude. And because so we also looked into the consecutive dry days, right? So the maximum length of dry days in any given year. I mean, in any from 1951 to 2020, and then we can see that the maximum length of consecutive dry days are decreasing in the Chesapeake Bay, with with most significant, especially in the western and the southern part of the watershed right here. And this is the trend, right? And so it's, oh, I put the wrong plot. So after that, we move into temperature, right? So for the temperature, the first thing we evaluated was that the minimum temperature. So on the plot on the top right here, it shows you the monthly maximum of daily minimum temperature, right? And then and then we calculated the trend basically. And on the bottom, we see this is the plot of the monthly, the monthly minimum of the daily mean temperature, right? So the monthly maximum of the daily mean temperature is increasing, and the monthly minimum of the daily, minimum temperature is decreasing, indicating the warmer nights that's happening, like within the Chesapeake Bay watershed, right, with significant trend. And when we did similar evaluations for the maximum daily maximum temperature, the trend was not significant. But if we look at the decadal averages, we can see that the decadal average of monthly maximum of daily maximum temperature is increasing consistently, like it is increasing slightly, although the trend is not significant, right? After that, why am I, oh, okay, I am going the right way. All right. Sorry. This is so one of the critical, like variables that agriculture producers, especially like apples, and then like grapes, they're worried about frost days, right, chill hours. So when we evaluated the frost days in the Chesapeake Bay, we can see that the frost days is decreasing over the whole Chesapeake Bay watershed, with high magnitude in Maryland, and then the southern parts. So that can have significance in these fruits, right, that need like chill hours. We similarly evaluated tropical nights, and we can see that tropical nights are increasing, right? And so the nights are getting warmer with significance in almost all of the watershed. Again, considerable trend in the eastern shore of Maryland, basically, right? And so that is where we see the most increase in the temperature of the basically these tropical nights. We also looked into growing season length, because this can impact our growing period, right? So we can see that the growing season length is increasing in Maryland with significance right here, and this shows the trend, sorry, the magnitude, right? So the growing season length is basically increasing most in the southeastern portion of the Chesapeake Bay. Sorry, it's from 0.00 to 0.08 like days per year. Yeah, so blue is like more, like so it is 0.06 to 0.08 days per year from 1951 to 2020. Good. Sure.
Basically, we are getting 1 day a year.
Yes. Yeah. Close to 1 day a year, like in the most intense areas,
One
like
day
per year. So yeah.
over that period.
Yeah. Yeah.
We gained over what, 50-year period?
Yes, in some parts, yeah, according to this analysis, 0.6 to 0.8, right? So yeah, like so 30 to 40 days, like 70 years. So if you do by 0.8, so like 30 to 40 days of growing season length has increased. That's what this data is telling. Yep.
Oh, okay, that's quite a bit.
Yep. Yeah, I hadn't evaluated the thought about that. Yeah, but yeah, that's true. Yeah. And then we also looked into growing degree days, but I didn't present that here. Okay, so that presents the first part of the studies. Again, these are studies that we just finished. I'd be happy to discuss more, and then present the results if need be. After that, the second part of the project, I'm going to briefly touch on the application of these climate data sets for hydrological evaluations, right? And so like hydrological evaluations of the past, hydrological evaluations of the future. So the first project that I'm going to talk about is a NASA project that we are currently working on. We are working on the upper Mississippi River basin, and then the goal of this project basically is to develop a high spatial resolution watershed model that can simulate carbon, so that we can look into like basically estimate carbon budgets for the terrestrial as well as the aquatic processes, provide ecological insights into identifying key patterns and processes that are governing these dynamics, as well as understanding and enhancing the aquatic as well as the terrestrial fluxes, right? Because like the carbons are sequestered in the terrestrial and like land surfaces, and then they are transported to aquatic mediums, right? So for this project, so the goal is to develop a very high resolution model, right? And so in this in the model that we develop, there are more, for people who know SWOT, it has more than 5,000 subbasins, right? These are all the USJ stations where we are calibrating and validating the model. On top of that, we are using a suite of remote sense data sets like ET, NPPC, LAI, yeah, like to basically constrain the terrestrial processes as well, right? So uh, we are currently in the process of calibrating the model, and then just showing some preliminary results on what we can expect, right? So the graphs on the left, it shows you basically uh, the skill, right? Basically how the model is performing in basically capturing the, what is that, evapotranspiration, LAI, NPPC. And after we properly calibrate the model, we can basically get a carbon budget for the whole watershed, right? So what is like NPPC in the terrestrial processes, how much is being respired, how much is being lost to groundwater, what's the lateral fluxes, what's the surface fluxes, and even in the aquatic medium, due to algae and all that stuff, like what's the growth, what's the loss, what's the decay. And we can develop spatial plots as well, right? Now we all know, and the reason why showed you this research is like, so carbon neutral is a big goal of Maryland as well, to reach by 2045, right? And agriculture as well as forested landscapes, we need to understand the overall carbon budget of these different landscapes, like yeah, carbon budget, to basically evaluate if we are reaching that a carbon neutral goal, as well as identify methods, like practices, land use change, cropping types, that can impact these carbon budgets. So one of the goals that I have, and that I'll probably that I'll work on next year, is to develop a high scale, like a similar project, like a high resolution Huck 12 based SWOT model for the Chesapeake Bay, or at least for the Maryland, right? And with that, the goal is to basically do similar analysis, like highly constrain the model, and evaluate the carbon budget. Like we can even look into water quality. And because the models are being developed at a Huck 12 basin, the recommendations, or the evaluations we can perform at a Huck 12 level. So that can be good for basically providing feedback, or suggestions to the the policymakers, or like whoever needs it the most, right? Okay, the second project that I'm going to talk about is is a climate change study that we did. Basically we evaluated the impacts of climate change under project under CMIP 5 on the surface and groundwater resources of the lower ACF river basin, right? So what we did was we basically developed a surface, like the region right here, it's highly like ag dominated, irrigated through an aquifer system that's very close to the surface, basically a superficial aquifer system, right? So we developed a SWOT model for the region, we developed a groundwater model for the region, and then couple the model to basically develop an integrated surface and groundwater model using SWOT mod flow, right? After developing the model, we calibrated the model for stream flow, we calibrated the model for groundwater levels at 6 stream flow stations, more than 300 groundwater level wells. And then we evaluated basically simulated climate change projected under CMA 5, and then evaluated the impacts, right? So I'm just going to show you quickly the results. So we looked into how the monthly flows would change, right? The lighter blue represents the range of the change, and then I think the green represents the average of the change. So it would tell us, like in which months we can expect an increase in monthly flows, as well as a reduction in monthly flows, right? We also looked into low flow conditions. So what we did was we evaluated what the 7Q10 was under baseline conditions, and then we evaluated if the number of days where the flows would go under 7Q10, right? And so like the low flow conditions for all of this in the 6 stations right there. Along with that, we also looked into how the groundwater levels would change in the region. We basically under different scenarios, we evaluated basically where the groundwater levels would change, and then what the groundwater, and like what the changes in the levels would be, right? And although like the magnitude could not be like it has high uncertainty, the regions could provide indications on where we need to where the climate change impacts will be the most, and then plan accordingly. So the third part of the project that I'm going to touch on is basically improving process representations in hydrological models, right? So now we all know we use hydrological models day in and day out to do all these climate change evaluations, right? SWOT is one of the widely used models in doing climate change studies, right? But understanding the process limitations within the model, and quantifying that as uncertainty, and as well as improving the process representations, right? So that we can reduce the uncertainty, as well as have better confidence in the estimates, is critical, right? So one of the project that we finished, or like we could even even currently working on, is basically developing a new forestry module within the SWAT interface, right? So SWAT, it's great for agricultural land uses, but the forestry module within SWAT has many limitations, right? So I've listed it right here, right? So carbon allocation is inadequately represented, and it does not partition into root, shoots, and leaves. Like the litter fall is, there's issue with litter fall. There is issue with forest initialization. So we developed a new forest module that's based on 3PG. That's physical based, just a forest module. So we incorporated that, and then we tested the module at these field sites right here, right? And then we the model evaluation showed that the model could perform better than the default SWOT module in replicating this forest dynamics, as well as like including carbon sequestration, carbon losses, partition into by like leaves, stems and roots, and all that stuff. And after evaluating at the field scale, we basically wanted to test it at a watershed scale as well, right? And so we did a case study in the St. Croix River Basin. The details in the left provide you like how we build the model, basically like 419 sub basins. That's the year we simulated for, like, so we evaluated our stream flow at 5 stations. All on top of that, we use a leverage remote sense data sets like MODIS NPPC, MODIS LAI to constrain the terrestrial process. And then we also compared the forest biomass data sets against other processes, right? And then we also did for water quality evaluation. So after calibration and validation, we could so the basin average, the model could really replicate the basin average NPPC, right? Along with that, it performed comparably against other observed data sets, and with that, it was able to provide us with a spatial distribution of the difference in above ground biomass, basically forest, right? And not just that, we evaluated, going the wrong way, here we go. We also evaluated how this new forest module impacted the different hydrological processes in this forest dominated watershed, right? And so if you look at the soil moisture, we know that forest retain a high soil moisture, right? And then there is not much superficial flow. So with the new module, which is represented in green right here, we saw a reduction in superficial flow, we saw increase in lateral flow, we also saw an increase in soil moisture. So along with the climate the carbon part, so the incorporation of this new forestry module could be beneficial in basically like reducing the estimate, like in the uncertainty, even like in the hydrological and then the water quality evaluations, right? And on top of that, so we all know forest is a critical source of carbon sequestration, right? And then most of the forests in US are managed forests, right? And so with this module, and then with the new management practices that we're incorporating into the model, we can run scenarios where we can test different tree types and then see how this would change the carbon sequestration potential, right, under different climate, under different soil, and then the regions as well, which can basically help with the climate improving the carbon sequestration. I did not put it here, but we are also, as Dr. Shrivastava mentioned, we are also working on improving the wetland module. So similar to forest, the wetland module in SWOT is very limited, right? And then it does not incorporate many of the nitrogen, phosphorus, and then the carbon processes. But we all know wetland is the new thing, right? Like that's like people are really looking into from a carbon from a carbon management perspective, right? And even from water quality. So we are working on improving basically developing a new wetland module in SWOT that's based on wet qual, and testing the module to see how that performs, right? So that in a gist provides of all the work that I'm doing on and brings it to the end of my presentation, basically.
We have some time for questions. We have a group that's coming in at 10 till, but till then.
Yes.
So,
Hi there. I have, I guess, 2 questions. One, where is the lower ACF
River Basin? So that's in
I don't
it's
think you touched on that.
sure, yeah. So it's part of so it's in Georgia. It touches Georgia, Alabama, and Florida. So I did my PhD at Auburn, right? So that was the hot area where I worked on. So it's part of so there's this basin called the ACF River Basin, Apalachicola, Chattahoochee Fringe. So it's basically on the southeastern United States.
Okay, so it's 3 and 1. Also, for the upper Mississippi Basin, is there any is there like one static value for like each like type of crops, say soybean, corn, and pasture, or are there grades based on the based on how they're managed, as in if they use cover crops or have conservation tillage?
Yeah, so those are the intricate, like, and when you say value, I'm assuming you mean like growth, productivity, like yield. Is that what is value?
Just
Yield?
yes,
Would that be yield?
just model parameters.
Output? Okay, no, so it's dynamic, right? So I mean, there are limitations, because we are, modeling such a big region, right? So there are limitations, to what we can incorporate, right? And so, for such a big watershed, we cannot really tell, like, at least at this point, from where they're doing conservation tillage or where they're doing no tillage, and of course that can have an impact on, carbon, right? But that those are the uncertainties, that are within the model. We have tried to incorporate like a very detailed crop rotations, like, so we evaluated 20 years of data, like, like crop data, like CDL, like, like satellite data, looked into what the major crop rotations were within each of the Huck 12s, right? And then we incorporated the major crop rotations. On top of that, we are, using these remote sense data sets, right? Like LAI, NPPC, and then we also know the crop productivity, and that will, help us, constrain the productivity, so the amount of carbon that's being sequestered, right? And then, for the carbon loss part, there are data sets that are coming, like, below soil carbon storage, like, so like we haven't incorporated that, but that's something that we could look into. And on top of that, there are riverine, like carbon data sets that we use to constrain the model processes. So we try to constrain as much as we can, but, as you mentioned, like, tillage, types of tillage, so those are the uncertainties that we have to deal with when doing this large scale evaluation.
Ritesh, can you give us a sense of how much data you sieved through? Because you looked at multiple graded data set for 40, 50 years.
Yeah.
And all these weather stations
Sure.
spread throughout the Chesapeake Bay. How many gigabytes or terabytes of data?
Well, it's not terabytes, so now, because the data comes in a good format, right? And like netseria, so like, it's really compressed, so we need to, like, extract it, but it's so it goes to gigabytes, and then the evaluation takes long, especially if you're not parallelizing the processes, like, so if I'm doing, those one of those, like the precipitation, it can take a day to evaluate, but, it can be fast, so downloading is where it takes time, and of course understanding the data set, is where it takes time, but, it's not, I mean, it goes to maybe 100, 200,000, I mean, like gigabytes, 3, 4, 700, 800 gigabytes, maybe like a 1 terabyte, like, including all the 7 like NCLIM grades for the whole, so, but it's very manageable.
800 gigabytes of data is not small to handle.
Yeah, but, now with R and all, it makes it easy for us, like, because they provide it in such a way, so it's not as bad. Any other questions? Yes, Jen. Hey.
So, you talked in the beginning about different types of graded data sets,
Uh-huh.
right, that you were looking at and evaluating how good they were, right?
Yeah.
But in terms of the differences in, the ones that performed really well,
Uh-huh.
was that just up to resolution of the data?
No,
or
it's on the methods, right? So the two, best data sets that, performed well were the NCLIM grid and then the Prism data sets, right? So both are based on the NOAA GHC and D station. So it's just statistically, as you can see, like, as you go into reanalysis, which is basically, provide the data sets to models, and then model providing the spatial resolution, the skill goes down, right? But the two data sets, those are based on statistical, and Prism especially, like, temperature and precipitation can vary like drastically with altitude, right? And then I don't know how, but Prism, account for that as well. So that it's basically to the methods, so the resolution would not, because those are the high resolution data sets. They provide data set at, like, close to 4 and 5 kilometer data sets. The ones that do not perform well are, like, 28 kilometers, and that could be the reason as well, right? When we're evaluating at a 28 kilometer grid, we're averaging the whole area, right? Although we might have the observed data sets to, like, go that high of a resolution, we might not, but, so it comes down to methods, like, on how they are basically interpolating the data sets. Yes.
So that data on the Chesapeake Bay with all the trends and
Yes, sir.
climate and things, it seems like that would be really interesting for farmers and environmental scientists and such. In your position, I'm not sure I understand your position in the college, but are you trying to somehow make that available to
Yeah.
like in a web map where you can like zoom in and say, what is my region doing for all this, expected extreme events and such like that? Because I think that can really bring it home to people. It's like,
Sure.
I fully understand the context of the project and where that fits.
Sure. No, I mean, that was the goal. Like, so, I mean, I'm very lucky in that, so my research is very open. Like, I can do, like however I want to do it, right? Because like, of course, it's related to climate, right? So, but, the goal is, of course, we need additional verifications, like, to make sure like what we see are correct, but, with that, basically, provide this historical evaluation as a gridded data set. I mean, and I don't know how we would provide it, but the goal is that, maybe other faculty or other people can use it so that, they can use this indices as well as the trading indices, or even like, farmers, like, on how it's. But the next process that we are going to do is we're going to do a similar evaluation, but for the future climate. First, so we're going to evaluate CMIP 6, and then, basically, hopefully, like, come up with, or I discussed it with Dr. Shafasta the other day, like, come up with change factors. So under future climate, what would be the change factors for these different indices, right? And that can be very valuable data set as well. So we do plan on working this, of course, the paper part is there, but, the more it can be used, the better it is anyway. So, and that's the goal.
The Thesis project is also going back to feed adults project on climate vulnerability assessment. So all the data is going to do that. How the climate is going to
Is there a way to like kind of get it out in the public?
Yeah.
Like, I've been working on this project with some GIS people from the Nature Conservancy, and they made this map that you can now, anybody can go and look at like how things are gonna change, and it's all kind of accessible, and there's a lot of really great stuff in there, and it seems like it wouldn't be that hard to get it into like a GIS thing that
No, I mean,
could use it, Just an idea, very interesting data sets.
Well, there may be additional questions, but I think we're going to have to bring this portion of our session to a close. So let's thank Ritesh again for a great
Thank you.
presentation.